All right, section 5.7 is some more identities. These are the double angle and half angle identities, which we'll use to prove some more different identities, and we'll also use them to find exact values of angles that are not on the unit circle, but that we can get from ones that are on the unit circle. So we'll start with the double angle identities. On page 258 in your book, it gives you some proofs of those and some where they're deriving them. They use the sum formulas that we already learned to derive the double angle identities. So here they are. The sine of 2 times a variable, u. I think your book uses x, but the sheet that I gave you uses a u, and it doesn't matter. But sine of 2u equals 2 times the sine of u times the cosine of u. And the cosine of 2u, when you use the double angle formula, this is what you get. This cosine squared u minus sine squared u. And you can use those Pythagorean identities. Remember that we have that the sine squared u plus cosine squared u equals 1. That's a Pythagorean identity. You can use that to get this in two other forms. So these are the double angle formulas. So we need to know those. And then the other ones we have are the half angles. And you use your double angle formulas to get the half angles. That's also in your book, so make sure you look at how it's derived. The way your book writes it is the cosine of x over 2, that's why it's called a half angle, is equal to plus or minus the square root of 1/2 times 1 plus the cosine of x. And the sine of x over 2 is plus or minus the square root of 1/2 times 1 minus the cosine of x. Now, your sheet that I gave you writes it a little bit differently. Instead of saying half angles here, it gives you twice of it here. That way you don't have to look at the fractions as much, and it also puts a square in there so that you don't have the square root. So the way they write it is the cosine squared equals 1 plus the cosine of 2u over 2, and sine squared u equals 1 minus the cosine of 2u over 2. So this is the way your book writes it. This is the way the formula sheet I gave you writes it. They're exactly the same thing. Make sure you look at them and understand that they are the same thing so that you can use them either way. Now, we've got all these formulas. So how are we going to use them? Well, let's say we want to know what the cosine of 11 pi over 12 is exactly. We don't want a decimal approximation. We want to know exactly. Well, we know that 11 pi over 12 is 1/2 times pi over 6. So we can use a half angle, or times 11 pi over 6, sorry. So we can use a half angle formula for that. So the cosine of 11 pi over 12 is equal to the cosine of 1/2 times 11 pi over 6. So the first thing we need to look at is decide what quadrant this angle's in. This angle, 11 pi over 12, if you think about it, your unit circle, you realize that this is in the second quadrant, which means that the cosine is negative. So our answer is going to be negative. That's why we had the plus or minus on those half angle formulas, because it depends on what quadrant you're in. So our cosine is negative, and then we just have to plug it in the formula. The square root of 1/2 times 1 plus the cosine of 11 pi over 6. Okay, so we take this angle, plug it in here, and then we just calculate this out. Well, we know that the cosine of 11 pi over 6 is the square root of 3 over 2 from our unit circle. So we simplify this out, and we get, well, let's go over here and get a common denominator first. So we have negative the square root. If we get a common denominator here, that makes this 2 over 2. So we have 2 plus the square root of 3 over, and then our denominator is 2 times 2 is 4. So that gives us negative the square root of 2 plus the square root of 3 all over 2, because the square root of 4 is 2. So there's our exact value. That's where we want the answer. Don't try to get a decimal approximation when it says exactly. All right, so we did some more of these with the sum and difference. Basically, you just look at the angle and try to figure out if you can make a sum, a difference, a double, or a half of it, and then use the proper formula so that you can get the exact value with stuff from the unit circle. What if we want to prove an identity? What if we have the cosecant of 2 theta equals the cotangent of theta over 1 plus the cosine of 2 theta? Well, remember we said we usually start with the most complicated side and we work our way to the other side. So we're going to start with the cotangent theta over 1 plus the cosine of 2 theta. So it's easiest to work with things a lot of times if you just put it in cosine and sine. So we're going to do that. So we're going to have cosine of theta over the sine of theta, because that's what cotangent is, over 1 plus, now this one you have choices. We know there's 3 different ways to write the cosine of 2 theta, so you just have to kind of experiment. You should be able to get to the answer in the end with any of them. It just depends on how many steps. Like we've talked about a few times, there's lots of paths to get to the right answer, but sometimes the path is easier and shorter, and sometimes you take a long twisty road to get there. So in this case, I'm going to choose to use 2 cosine squared theta minus 1, because that'll get rid of this 1 here, and then I'll just have the cosines and sines to deal with. So if I simplify this, I have the cosine of theta over the sine of theta times 1 over, and here the 1's cancel, so I'm left with 2 cosine squared theta. Okay, see, I just took this. Remember, this is divided by this, so that's multiplied by the reciprocal. So now my cosines cancel, so I just have 1 cosine left, and I'm left with 1 over 2 times the sine of theta times the cosine of theta. And I say, well, that looks awfully familiar. That's a double angle formula. So now I have 1 over the sine of 2 theta, which is the cosecant of 2 theta, which is what I wanted to get. Okay, make sure you know that are familiar enough with those formulas that you'll recognize that. Let's try one more. This one I want you to try on your own. So what I want you to do is, after you've copied this problem, I want you to pause the video, work it out, and see if you can get it, and then we'll come back and I'll show you how to do it. So go ahead and pause it and work this one on your own. All right, so hopefully you've paused it and you've worked it on your own. There's lots of ways to start it, to get from one side to the other. I'm going to start with this side this time because I can use a lot of my formulas. Here I can use a sum formula, and then I'll end up using a double angle formula also. Remember, there's not one right answer. As long as you have gotten from one to the other without assumptions and things like that, then you're good. So I changed the 3 theta to 2 theta plus theta, which gives me my sum formula, cosine of 2 theta times the cosine of theta minus the sine of 2 theta times the sine of theta. And then I'm going to use my double angle formulas. In this case, I'm going to use the cosine one because I've just got cosine here. So I'm just going to use the cosine one. And as you do more of these, you'll be able to pick out which ones you need to use easier and easier. So that's why we need lots of practice with these. So I put in my double angle formulas. Now I just multiply everything out. Okay, now I've got this sign in here that's kind of throwing things off. So I want to use my Pythagorean identity to change it to a cosine. And then after I've done that, I end up with, there's my cosine cubed. I have 4 cosine cubed theta, and then minus 3 cosine theta, which is what I had at the beginning. So that's what I wanted. So I used my sum formula, then I used double angles, and then I used Pythagorean. They're all going to mix up. You just have to kind of pick and choose. And like I said, there's multiple paths to get there. So you're going to have to get familiar with these and kind of look and play with it and see how much you can get. Make sure you've read this section and got good notes so that we can go over this in class the next class period.